Welcome to part 3 of module 3. So far we have discussed how we can select the best model, especially forward selection, backward elimination, stepwise regression, and also we have discussed how we can select the best model based on adjusted R-square, MAC, CM, CM minus M. If this is close to 0, that is the model is the best one. We have also discussed PRES, PRE statistic. We have also discussed AIC value. If this value is lowest, then we can select the best model. And lastly, we have checked that how we can check the normality assumption, especially QQ plot. This plot, if this is the QQ plot is something like that, like this, that is normality assumption satisfied. And especially if we plot residual versus y hat, then we should expect a completely random to become constant variance. If there is any upward trend, or if there is any funnel shape or something like that, or upward trend or lower trend, that means constant variance assumption does not satisfy. If this is the case, in the previous slide I have shown you that we may need to transform the y, so it can be transformed, for example, log of y. If this is the case, then we cannot use least square estimator, and that in that case probably we need to use the another method. That method is called weighted least square. The ordinary least squares method produces insufficient estimates if the assumption of homoscedasticity, that means constant variance, violates. The weighted least square method can be used to achieve a constant variance, and then the OLS method can be applied to the transformed model. So first of all, we need to transform y into something else and then feed the OLS to get the constant variance. If the observations are independent but have different variances, then theoretically both sides of the regression equation can be multiplied by a matrix of weightings cross representing the inverse of the individual variance for each observation. In practice, the exact weighting are often unknown and must be estimated. Correlated errors, the weighted least square approach generalizes easily to a multiple regression model with correlated errors. That is where the error variance are not constant and where the errors are not necessarily independent. So correlated errors, that means autocorrelation. So this is the procedure of weighted least square. We are not going to discuss more about details about the weighted least square methods, but just make sure that if the constant variance assumption does not satisfy, we can transform y to something else and then use the OLS method so that the constant variance assumption satisfied. In addition to the residual analysis to verify the model assumptions, other graphical and numerical diagnostic methods are useful in the understanding of the sample data. So one of them is outlier. An observation is called outlier if it is corresponding residual, that means EJ, the standardized residuals or the standardized residual QJ, or the standardized deleted residuals we'll discuss soon is far greater than that of the rest. So if this is the case, residual is higher, that means this is an outlier. The preferred residual is the standardized deleted residuals. An outlier can perhaps be defined as a point which lies between the 3 standard deviation away from the mean of the residuals. So that means if any of the residual is less than negative of 3 or greater than 3, then we can say this is an outlier. The presence of an outlier indicates that the corresponding data point is not typical of the other data values. Further examination of outliers is essential to find out why they are so different from the others. Standardized related residuals, here is the formula. Formula is the YL if L, look at here, if L response deleted, the standardized related residual is YL minus, if we delete the Lth observation and calculate the estimated value, and then sigma hat, and then calculate the sigma hat, deleting that observation, and then calculate the hat matrix and square root of hat matrix, then you will get the TL. It is known as TL that has a student t distribution with n minus k minus 2 degrees of freedom. Any observed TL that is greater than 2 indicates that the associated data value should be clearly scrutinized as a potential outlier. Standardized related estimates are cumbersome to compute by hand and are the best using a computer. And we probably remember the hat matrix is this here, and YL is the response value for the Lth. YL is the response value of the Lth observation, and Y hat L minus 1 is the estimated value of the Lth observation after deleting the Lth value, and sigma hat L minus 1 is the standard deviation of the Lth observation excluded, and Hayes LL is the Lth diagonal element of the hat matrix, and you already know that how we can calculate the hat matrix. Another one is called the hat values. We already know this is the hat values. And we also calculate the hat values. The Lth diagonal element is called the leverage or the hat value. It is known as that if we add all of the diagonal elements hat values, then you should get the P. So that means if you calculate the Hayes bar is P by N. P is the number of parameters divided by total number of observation is the average of the main diagonal elements Hayes. An observed response is said to have an unusual value if the associated diagonal element of Hayes is greater than 2p by n or 3p by n. Any such data point having unusual, it can be large or small, is called a high leverage point. So let's say if I go back to my R, so I think I have that example. Add values, let's say if I have that on. Okay. Look at the hat values here. So hat values here. So these are my hat values. And what's the condition? It says that P by N. P is in this particular example, P value is P is only 2 because I have included only one independent variable, that is x2. P by N, so that means 2 divided by N is 20. P by N, it is P by 2 by 20. So this is 0.1. So that means if any of this value, what is the criteria? Criteria says that an observed P by N is the main diagonal elements. If any observed response to have unusual, if the associated diagonal element is 2p by n or 3p by n. So 2p by n, that means this is 2p. So 2 times p by n. So this is 0.2. So that means if any of the hat value is greater than 0.2 or 3p by n, that would be our 0.2 or 0.3. So now look at here. If any of this is greater than 0.2 or 0.3, that is a outlier. So in this case, probably none of them 0.2 or 0.3. So there is no outlier in this particular model. So this is the hat value. Another one is identification of influential observation. A sample observation is said to be an influential observation if the exclusion of the observation from the analysis leads to very different conclusion than if it is included. So the next one is called the Cook's distance. For the Lth observations, the Cook distance is generated by QL. You probably remember QL is the studentized residual divided by P. Hence AL is the Lth diagonal elements of the hat matrix. CL is a measure of the difference between beta hat, and if the Lth observation is deleted, and then calculate the estimated value. A large value of CL indicates that the estimate of some or all of the regression parameters will change substantially if the Lth observation is omitted from the analysis. Sometimes CL is considered to be indicative of an influential observation if it is greater than F 0.5 P NP. So let's say first calculate the Cook's distance and compare with that value. So if it is greater than that value, then this is an influential observation. So let's say in R it is not that much difficult. If you just look at here Cook's distance, so this is our model here. If I just calculate Cook's distance, and if any of this is the Cook distance, if any of this value is greater 0.5 P and n minus P, then that would be outlier. So now look at if any of this observation is greater than 0.72. So none of them is greater than 0.72. So in this particular case, we don't have any influential points. So influential point in this case is that if we deleted that observation, the parameter estimation will be changed. The next one is called defeats, difference in the fitted value standardized. So defeats value is calculated for the Lth observation is YL minus YL. That means the fitted value including YL, and YL minus 1. That means fitted value excluding L, and then excluding L, the estimated sigma hat estimated standard error, and then the square root of the Lth diagonal element. If the absolute value of defects is large, the Lth observation is said to be an influential observation. An alternative formula is given by, this is an alternative formula, TL square root of HLL by 1 minus HLL, where TL is the studentized dilated residual for the Lth observation. Sometimes the Lth observation is considered to be influential if the absolute defects value, if we calculate the absolute value, and if it is greater than 2 square root of P by N, then that is an outlier. So let's look at our example defeats. So defeats, our model is BF dot LMX2, that means only X2. If we calculate the defeats, so this is our defeats value. Now we are calculating 2 square root of P by N, 2 square root of P by N, because we'll need to compare that one, 2 square root of P by N. If any of this value is greater than that, so these are the value here, and if any of this value is 0.6, if any of this value is greater than 0.6, I think this one is closed, this one is very, so this observation might be an outlier, because 0.66 is very close, probably not be an outlier, but close to an outlier. So this is how we can check if there is any outlier, if any particular observation is outlier or not. So this is the defeats. So we have learned Cook's distance, defeats. We have learned how the normality plot to check the normality. We have learned how we can check the homoscedasticity, and we also learn how we can check if there is any influential observations in the data. So in the body fat data set, in the data set, here is the QQ plot. Here is the residual versus a particular residual versus y hat, residual versus y hat between this one and this one is the same. And here is the Cook's distance, and here is the defeats. So let's say I have that program in R, so I can show you. Look at here. So this is my QQ plot. This is my QQ plot here. This is the residual versus fitted value y hat. So it's completely random. And this is the plotting of Cook's distance. So Cook's distance, so maybe here these two observations, so that means 10, 13, 14, these two observations may be outlier. So look at here, if I calculate this one here, so this is 0.72. I think no, they are not outlier, because according to the definition, if any of these Cook's distance is greater than 0.72, then this can be outlier. So this basically up to 0.20, so there's no outlier here. Now look at here the defeats here. I am going to plot defeat. This is the defeat value, and if any of this defeat value is greater than that, that should be an outlier. So 0.66, this one might be I think this 14. So 13th or 14th observation might be outlier. So if this is the plot here, this is the plot here. So in these examples, this one is the QQ plot. That means this is normally distributed. No pattern here, so that means is constant variance assumption satisfied. Cook's distance and defeats shows that observation 13, 14, but we have checked, probably they are not that much outlier. So these two observations slightly larger than the rest, but not that much higher. So, and we have checked that these are basically not that much outlier. So in this particular data set, we don't have any outlier, but if for any data set, we can easily check if there is any outlier or not. And another important term is called the multicollinearity. Multicollinearity occurs when there is a linear or near linear relationship between two or more regressors. That means x1, x2, x3 up to xk. So if they are highly correlated, that means we call them multicollinearity. In such a case, the X transpose X matrix becomes ill conditioned, that is, the determinant is 0 or close to 0. As a result, its inverse becomes unstable. Its inverse becomes unstable, which affects the parameter estimation, because the parameter estimation is X transpose X inverse X transpose Y. Since its determinant is 0, this is very unstable, and it affects the estimates of the parameter. Multicollinearity is most likely to occur when similar variables are being collected. For example, surveys on opinions or attitudes. How they say, if the two variable here, how do you rate the government and how do you rate the prime minister? So if we included both variables in the model, there may be a case that they are highly correlated. Consequence of multicollinearity: as said, X transpose X matrix becomes singular, and so the least square estimator does not exist. If one or more exact linear relationship among the regressors, then this will not be happen. That means least square estimator does not exist. For linearly exact linear dependencies, variance of beta hat to be large, and hence confidence intervals will be too high, so results are imprecise or unreliable. The t statistic for testing the significance of beta I will be too small, and hence leads to a false conclusion of acceptance of the null hypothesis. Estimators may be too sensitive to the addition or deletion of a few observations or exclusion of an apparently insignificant variable. Estimators may be a wrong sign, and calculation of the least square estimators become too sensitive to rounding errors. So these are the consequences of multicollinearity. A prediction of a future response in the presence of multicollinearity will still be satisfactory if this is connected to the regions of X space where the multicollinearity holds approximately. Now, the thing is that how we can determine the multicollinearity. So there are three ways. One is the simple correlation coefficient. A commonly used rule of thumb is that if a correlation coefficient between two regressors is greater than 0.8 in absolute value, then there is a strong evidence of multicollinearity. Inverse of the correlation matrix. The diagonal elements of the inverse of the correlation matrix greater than 5 indicates the presence of multicollinearity. So that means you can calculate the correlation matrix first and then calculate the inverse of this. If any of this value is greater than 5, so that means the indicates the presence of multicollinearity. And the other thing is that the characteristics root. So that means the condition number. So here is the formula. Psi is the lambda star suffix divided by superscript. So if this is the case where this one is the highest and this one is the smallest characteristics roots of X transpose X. So we need to calculate the X transpose X matrix first and then calculate the characteristics root and if we divide the highest one divided by lowest one, and if that value is less than 100, the problem of multicollinearity is not serious. If it is 100 to 1000, the problem is moderate to strong, and if it is greater than 1000, then there is an acute problem of multicollinearity. The condition number for each of the characteristic roots can be defined as this way. The number of size is that is greater than 1000 is useful measure of the number of near linear dependencies among the regressors in X. So I will show you in a minute how we can calculate that multicollinearity. So let's say if I go back to my R, I should have example 1. Yes, condition number. Let's say if our model is included 3 variables here, x1, x2, and x3, and this is our X matrix, C bind of X matrix. So x1, x2, x3. So here is the Eigen value. The formula here Eigen. This is the T transpose X transpose X. The Eigen value, the comma Eigen, and if I write here $sign values, and it will give us the Eigen values. These are the Eigen values. So E, V, A, L, S, these are the Eigen values. Now, so there are here these are the Eigen values, and if we divide the maximum Eigen value by divide by minimum Eigen values, you will get the condition number. So condition number is less than 1000. So that is a moderate form of multicollinearity. And the other way it was this is the moderate form of multicollinearity here. And look at what is so we got here condition number, we got here 679. So let's say in that data set, what was here? Okay, so look at here the condition is 679. So that means suggesting a moderate multicollinearity. And the other way we can calculate the correlation matrix. If any of the correlation is greater than 0.8, so this one is greater than 0.8. So that means x1 and x2, these are basically highly correlated. And so we got the multicollinearity here. And other thing is that we can calculate the inverse of the correlation matrix. So we can get the correlation matrix first and the inverse of this correlation matrix, and then we can calculate that if any of these values, so these values are greater than 5. So let's say what is the same or not in our data set. We already calculate that Eigen value, that is 679. So now this is the correlation matrix. So correlation X mat here, if we just core X mat, then we'll get the correlation matrix. Just if I write here R, yes, so that is 0.92. So x1 and x2 are highly correlated. So that means either we include x1 or x2, not both, because they are highly correlated. And Look at if I use solve of R, that means all of these is, especially the diagonal, are greater than 5. So that means the multi-collinearity problem here. 148, 17, and 23 if we were, is not the same. I think, yeah, okay. I think this is not right. So it is not 148. It should be, first one should be 708. So this is 708. But whatever it is greater than 5. So all integers exceed 5. So that means there is a problem of multiplicativity, and the other things we already done this. In this particular example, the condition number is 679, which is less than 1000. So that means there is a moderate form of multicollinearity. So this is our module 3. So we have discussed selection of the regressions for best model. We have discussed the coefficient of multiple determination, mean square residual, CM statistic, Bayes statistic, AIC. And in the procedures of model selection, we have discussed all possible regressions, backward elimination procedure, forward selection, and stepwise regression. And I have shown all of you in R using the body fat example, where we have we got the best model including only one regressor, that is X2. We have also discussed how we can check the assumptions using residual, and we have discussed a little bit about the weighted least square, especially if the constant variance assumption does not satisfy. And we have discussed the other diagnostic method to check the assumption, especially outliers, standardized deleted residuals, had values, defeats, and lastly we have discussed the multicollinearity. Thank you very much.